You put it in a small vial and then put it in that UV spectrometer, and you see what is the absorbance of that, and it will be constant for a while, and after that it will be the saturation will takes place. And these UV spectrometers of different sizes that are available in the market, for example, UV Spectrovis Plus is a very tiny instrument, and which is affordable also. Within 1 to 2 lakhs only you can get it. And here is a small space where you can insert the cuvette, okay, and measure the UV spectroscope. And there will be a lamp. What is there inside is a lamp, and there is a small slit, and there is a dispersion device. Dispersion device could be a grating or a small prism which can be oriented. So you can have again a slit which is what you can call a wavelength selector, because all wavelengths will be falling there. Which wavelength you want exactly? So this will be moving, so that the same whatever wavelength you require, that will fall on the sample and that will go to the detector. But most of the times we use another system. If it is a bigger system, then we will use a reference cell. Always we go with a reference cell of a blank sample with respect to your sample, then you will find out. Otherwise, in this case what happens is, whether that is given by the solvent or your material, we don't know. It's a combination of that thing which is detected here. So if you want, then what you have to do, you have to put a blank. First record the spectrum, take the data, again put a sample with the nanoparticles, again take the spectrum, again overlap, remove you have to do certain calculations to arrive at the absorption of the particles only. So here in this case you will have a reference cell. Directly you can nullify the effects of the solvent, and directly you can go. Usually they use alcohol or hexane or or water. So these three will be used as a reference cell to remove that. Okay, and you can have if it is a only ultraviolet spectroscopy, you will have ultraviolet lamp. Otherwise UV vis it is there, then ultraviolet lamp and a visible lamp. So after the ultraviolet lamp, immediately that will shut off, and then UV visible lamp will glow on. So the spectrum for a whole UV to visible will be carried out. So dynamic light scattering is another interesting spectroscopic technique, where you can find out the particle sizes, as well as uh, uh, of course the smaller particles will have more dynamics related to that. There is a system called zeta sizer. So zeta sizer is the one which tells you about the size of the particles as well as the charge that is present on the particles. Okay, so that is based on the principle of DLS. So you can see the bigger particles have slow movement, and with a particular laser, usually not a red laser. They use only for dynamic light scattering. They use red laser. Otherwise, a green laser 532 nanometers will be used. So smaller particles have more scattering, and you can see lot of distribution that you can get it with that. And different sizes of the particles you can estimate. But this size, when you compare with that of a SEM or TEM picture, you will see a different thing, because here the instrument doesn't know whether it is a single particle or a combination, like a uh, agglomerated particle. It doesn't know. It simply measures the diameter, and then simply it will say that 50 nanometers. You may think that, array, I have done particles, I have seen the SEM, it is about 10 nanometers. Here it is saying 50 to 100 nanometers. How come it is? So if the particles are charged, obviously when they are moving dynamically, they try to collide and they form agglomerates. So agglomerated size may be the thing which this is estimating. So usually what they put is, they put a small stirrer bar at the bottom. So continuously that will be rotating, so that the particles never settle. They will be floating around, and a laser light will be there. So with this one they will try to detect the size, effective size of the particles, whether it is a agglomerated or a bigger particles. Okay. So this is a DLS instrument, very small, tiny instruments nowadays they are available. So you can see with respect to time also, if there is any reaction going on or the size of the particles are growing. Suppose you have taken high concentrated liquids and you have added, you see that slowly it is growing. So if you want to see the dynamics of that, how it is growing, 1 minute, 3 minutes, 7 minutes, every time you can see the distribution. Okay. So another interesting technique is Raman spectroscopy. So Raman spectroscopy will give you about the inelastic scattering that is taking place, and which typically uses 532 nanometers. And then you can see that the inelastic scattering mediated by the electronic polarizability of the medium. So both the polarization and inelastic scattering both are responsible for this. And a material or molecule scatters irradiant light from a source, and most of the scattered light is at the same wavelength as that of the laser source. So if usually that doesn't happen, if the same wavelength is being scattered, it's called Rayleigh scattering. So Rayleigh scattering again, it depends on the size of the particle and the wavelength with which we are doing that. Okay, and size is inversely proportional to 1 upon lambda to the power 4. So that's the Rayleigh scatter size. Okay, so that's how the wavelength and the size are linked there. But Raman scattering is the one where it's an inelastic scattering and different wavelengths will be produced. You shine one wavelength and you'll get a altered wavelengths. Okay, so if it is not the same wavelength, then it is Raman scattering, and that is very weak also. It is very difficult to identify these Raman lines. So Raman lines could be like this is the initial wavelength which you are shining at the particles. You may get anti-Stokes and Stokes. So what is the difference between Stokes and anti-Stokes? Stokes lines means always when you are giving a higher energy, you are getting lower energy signals, like you are giving ultraviolet, which is higher energy, and you are getting some photoluminescence in the visible region. So UV is higher and visible region or IR is a lower energy region. You are giving higher and getting lower, that is Stokes shift. Anti-Stokes shift means you are giving lower energy and you are getting a higher energy. How come it is possible? It is like a photon is absorbed, and by the time it is de-excited, another photon will come. It's like stepping. So 2 3 photons, and then the final emission is from the top to bottom. Okay, so that is called inelastic. I mean, that is called, you can call it as up conversion. Okay, up conversion process. Usually you are giving a more energy. Okay, the electron goes to the higher energy and then come back to the uh, yes. Stokes. So Raman scattering in crystalline solids, okay, you have different selection rules. Energy conservation has to be maintained, momentum conservation has to be maintained. Okay, selection rules should be determined for the crystal symmetry. All the crystal symmetry also one has to take care. Okay, I'm just skipping all this. There are various uh, for various materials you can find out the LO, TO type of modes. Okay, so there are various things you can calculate and you can just go through that. And infrared spectroscopy is also another technique. If you use Fourier transform infrared spectroscopy, so this spectroscopy technique is very much useful for determination of bonds, stretching, bending, and all types of bonds you can estimate within a molecule. And you can see this is the instrumentation where infrared spectroscope source, and then you will have a sample and a reference, and again it will be determined. So usually you have different signatures for different bonds. For example, nitrogen and hydrogen bond, which lies somewhere here, 3600 or so. OH bonds have a particular signature. CH bonds, triplets. So all this, they have a signature things. Okay, at a particular temperature, so they show this type of vibrations at this stage, and these vibrations are very much useful for determination. Like for example, we have the Indian Standard Time. Okay, every country has their own standard times. So how do you say that that standard time and my whatever watch I am wearing, my time and that time, how it is varying? So how do you ascertain the time? So the atomic clocks, actually they use cesium and some other atoms. They use it, they immobilize it with lasers, or you supercool it. And when you start increasing the temperature, for every particular degree, there is a particular frequency with which the atom vibrates about its own axis. So that is called frequency. With frequency is number of cycles per second. With that one, they estimate the second, accuracy of the second. From that one, the accuracy of time will come into picture. So Indian Standard Time, we are maintaining at National Physical Laboratory, my earlier employer, where we used to have that, still we are having another new system also, with cesium atoms are being immobilized, and then we check for the vibrations with which it works. Why the time is so important? So time is very much important for not for trivial things like my watch and your watch. If it is differed by 1 minute, doesn't matter for us, isn't it? But time matters when it is for a longer distances. If you are space travel or something, if you are doing, and if you want to estimate the distance, then the fraction of second it matters. Okay, distance is equal to speed into time. So if the time there is a fraction, then your calculation of distance, everything, speed you are anyway monitoring, the distance will be difficult. The instrument say that you have reached, but you have not reached that position. So in thousands of kilometers, then few hundreds of kilometers, there will be a difference in that. So in NPL, National Physical Laboratory in India, who is maintaining the Indian Standard Time, so they are maintaining up to 26th decimal point of a second, 26th accuracy of after dot 26th place. So that much accuracy is required, and that is the time which is given to the ISRO to launch their satellites. ISRO doesn't believe on somebody else atomic clock. Atomic clocks are maintained by many countries. They don't believe on other countries. Obviously, if they try to give a small variation in the time, our all space shuttles will be destroyed. It will never reach the destination. So we have to maintain our own thing. We should not believe others. Okay, and even if you want to convert, I mean, you have a laptop and at the right side corner you have the time, na? You just click it, it will show the world time and then it will show Windows time. You can change it to Indian Standard Time. It is www.nplindia.org, time.nplindia.org. If you do, okay, okay, just put it up. So you can tune down to our own time. So sometimes you may be facing difficulty, like you want to book a IRCTC ticket. By the time you open, all tickets have gone. You'll see that still it is 1 minute is there, but how come these fellows are maintaining different time like that? You will be unnecessary. You are scolding IRCTC, but IRCTC is not doing that. Your time is wrong. So if you maintain this time even for your laptops and desktops, so you will be synchronizing always with Indian Standard Time. Okay, and you see, just for observation, whatever time which is there in your Microsoft thing, just before switching to this and then refresh it, just see the time difference. You will see that there will be 1 or 2 minutes difference would be there. So if you try to take Windows timing and start doing your space experiments, everything will spoil. Okay, so never believe. You should believe on yourselves only. Okay, so this is what. Usually for infrared spectroscopy, formaldehyde is taken into consideration as a standard sample. So it has many bonds that you can just take it as a reference things. For example, CH2, symmetric stretch and asymmetric stretch, scissors type of, and CO stretch, CH2 rock, CH2 egg. So all these types of things are mostly existing in many other things, and this, that's why it is taken as a reference material for FTIR. And if you want to compare FTIR, because both are giving the different types of bonds only. So here you can see it is FTIR is more sensitive to functional groups, especially OH stretch, which is available in water, good for studying constituents of organic molecules. Here, Raman is more sensitive to C double bond O and C triple bond O only. So you can distinguish between diamond and amorphous carbon or graphite. So if you want to distinguish the difference, because it's always between carbon things, so Raman spectroscopy is used, and studying backbone vibrations of the organic chains. So there it is useful. Here it needs some sample preparation is required, because for FTR you use KBR and then you make a pellet and other things. There it is not required. So little bit of sample preparation is required. So here you can study the little bit of fluorescence light also. If it is giving a different wavelength, you have shined one wavelength and you are getting different wavelength, that also you can able to see, but here no such emissions will come out, and it is having good sensitivity, good microscopic technique also. Whereas here it is very difficult to observe these Raman lines, so you can say fairer sensitivity, and it's also one of the good microscopic techniques. So let us have a small break for tea, and after that we will resume. Okay. Uh, I'll quickly go through the various techniques, because we have demonstration also. I have given only 15 minutes now. That's what the organizers are saying. But anyway, So here is the difference between FTR and Raman, which is shown, and I think the slides I will share it to the organizers, and you can get it. Okay. So another interesting technique is fluorescence or phosphorescence, which comes under luminescence. So luminescence is a cold emission. What you can say, it is a cold emission. There's nothing heat is involved when it is radiating. Like if you try to heat a metal to very high temperatures, okay, you see that there is emission from that, light emission. But that is associated with the heat you are providing. That's called thermionic emission. And there the red hot of iron, or and then still if you increase the heat you will get white emission also, different emission colors, but that is proportional to the temperature you are giving. That you cannot call it as luminescence. But if it is a cold emission, it could be based on the reactions, or it could be like you are shining one wavelength and you are getting back another wavelength. So where there is no heat is involved. So non-thermal type of emission from an object, and preferably in the visible region, it's called luminescence. But nowadays the segment has increased, like ultraviolet luminescence, infrared luminescence also people are calling. So you can extend little bit, but in all the way it should be non-thermal type of emission. You should get it. Okay. So there are different types of emissions. Like if it is you are shining optical radiation and you are getting the optical light output depending upon the excitation. Like I am exciting with photon, then it is called photoluminescence. If I am giving electric charge or electric field I am giving, and I am getting the light, that is called electroluminescence. For example, your mobile phones. So you are providing energy through batteries and you are having a display. So that is electroluminescence. So there also material is being coated from inside. So that is DC electroluminescence. Similarly, LEDs also come under electroluminescence. You are providing electricity as excitation source and you are getting light output. And if you are giving cathode rays or the electrons, okay, then it is called cathodoluminescence. Like earlier CRT, cathode ray tube and other things, you have electron gun and a fluorescent screen. So with the different energy of the photon, electrons will strike and you will see. That's why old TVs, when there is a power off, it will put up into a small dot, and if you try to touch that one you will get shock, because everything is concentrated and that small dot, still it disappears, it contains lot of charges. So that is called cathodoluminescence. Radioluminescence means if you apply the higher energy radiations like X-rays, okay, you can call it X-ray luminescence or radioluminescence also. And chemiluminescence, if you see, you know the exothermic and endothermic reactions, like you are mixing two liquids, if the test tube is getting heated up, then you call it as exothermic reaction. And if the test tube is cold, then you feel it is endothermic reaction, like it is absorbing heat from outside. Why can't only heat? Why can't light? Suppose if I mix two chemicals and get a light coming out of that one, it is possible. So that is called chemiluminescence. Okay. And there are some bioluminescence also, some biological bacteria. You can see in WhatsApp videos, like some of the seashores in the night, blue algae is lot of luminescence, it is there. And these what do you call that? Firefly. Firefly, in Hindi it is called jugnu. తెలుగులో మినుగురు పురుగు అంటారు. I don't know how many people are from outside this state. You know the firefly you see in the fields. In the night time you see some of the insects, glowworms. They are and in some of the movies also nowadays they are showing this. So that is bioluminescence. Actually it secretes some organic chemical, like we get sweat and that that organic thing which is called luciferin. That's the secretion from that glowworm. So it secretes. But where is the excitation force? The temperature of the uh, body temperature of the insect is taken as excitation. So that's why you see then it glows and slowly it diminishes, because when it is losing the heat, so it will glow, and when it flies again it generates heat, so that is provided to that one, and again it will glow and it will come down like that. So it is very highly fluorescent, that luciferin. So similarly, that's called bioluminescence. So depending upon the source of excitation, you have number of names. You can triboluminescence, you give pressure and then you see some glow, that's called triboluminescence. Most of the crystals you will see, and even you see some of the that marble stones, when you try to strike it, okay, you see specks sparking, okay, that's pressure. Due to pressure you will get that one. So wherever you get light using various phenomena, then you can call it as that type of luminescence. Okay. So the only difference between this fluorescence and phosphorescence is if it is instantaneous emission, like you are shining something and immediately you are getting different wavelength, that's called fluorescence. Phosphorescence is the delayed fluorescence, like it is absorbing and it is delivering in the evening times, like night glow stickers, radium stickers and other things what you see. So it is absorbing, and then the absorbed radiation only it is emitting in the dark times, so that is called phosphorescent. So essentially how to make these materials is, you can dope an activator which is responsible for the color. So crystal is the one which absorbs the radiation and then it transfers the energy to that particular activator which glows. So you can have various numbers, various types of emissions, like band edge emission. If electron is falling from conduction band to valence band, it's called band edge emission. From activator trap level to the activator level, trap to the valence band. So these are various possible mechanisms one you can have in this. Okay, and depending upon the color of emission, there is a CIE colorimetric diagram where you can locate it and identify, because there are various shades of color. You see, we don't know the difference between yellowish green and greenish yellow. What is the difference? People write it as greenish yellow, and somebody is writing yellowish green or green yellow, yellow green. All look same, but has a different meaning. Like if you see this colorimetric diagram, which is approved by all over the world. So here is bluish green, blue green, green. This region is called green, yellow green, yellowish green, greenish yellow. So a slight change in the color will have a different thing, but we don't know the difference, so that simply we will write it as this color, that color. So, but when you want to publish a paper or you want to transfer a technology, if you write this loose language, nobody will um, appreciate that. You should use a common language or a code language. Okay. So here you have x-axis and y-axis. So if you say that I have prepared a material which is having green emission with these codes, x this much, y, xy coordinates this much. So where it lies, so that indicates to that person, okay, you are talking about this color which is located in this one. Even when you go for painting of your house, that fellow will show you a shade card and all numbers will be shown. You show this one, that depending upon that number, he brings that paint to you. So same thing here also. So this is how internationally it is approved. We use many colors which are not existing in international literature. For example, the color which this girl is wearing, you say cream color. There is nothing like cream color or beige color, okay, or apple green and all. These are our Indian language, okay. We use many words like that, okay. So, but they are not internationally acceptable. So we have to use something which is everybody is can understand that. Okay. So to have this type of photoluminescence, if you take a metal piece or metal thin film, and then if you want to go for a photoluminescence study, it is not advisable, because photoluminescence arises because of two reasons. One is defect or a dopant. Either it should have a defect or a dopant. Okay. Defect can exist if you have a semiconducting material. Okay. And if you have an insulator, then only you can have defects or dopants. If you dope certain element, it will form an activator level. Somewhere between the valence band and conduction band, somewhere it will form an either acceptor or donor level. In metal, it is not possible, isn't it? So metal, if somebody brings a metal and go for a photoluminescence test, it should not be done. Only thing is you can do if it has an oxide layer, which is pure metal you have taken, but there is an oxide layer formed on that one. Oxide can be detected, but not a pure metal. Okay, so either you should have a semiconductor or a insulator, because it can be detected only defects or dopant. So photoluminescence in semiconductors, you know that we can make many devices and we can run through that one. Photoluminescence spectrum at different temperatures is also nowadays very important. Usually we do room temperature photoluminescence to find out the defects and dopants, but if you do low temperature studies, then you can estimate the density of that defects. Suppose you made a single crystal, very good crystal with almost minimum defects, but you want to know that what is the number, or if it is minimal defects means how many number and what type of defects, the point defect or a Schottky defect, Frankel defect, what type of defect. For that one you have to go for low temperature studies. You have to go lower and lower, like up to liquid nitrogen or liquid helium temperatures. Then you can quantify about the peak. See, at 220 Kelvin also some broad spectrum is observed. So you can this is at when you go to lower and lower temperatures like 6 Kelvin, you see there are certain strong peaks have come up. So the area under the curve of these things you can calculate, and you can estimate the density of those defects, density and number also. So those things you can determine using low temperature photoluminescence. So this is the setup, consists of low temperature cryogenic cell will be there, your sample holder, and there is the whole thing will be immersed in liquid nitrogen. So the sample as well as the holder, everything will be at low temperature. Then it is like when you decrease the temperature, the motion of electron, everything will be freezed. Everything will be freeze. So they'll put it, and while exciting the material, they cool down the system. So all the electrons that have went to the conduction band, they will be freezed there only. So then they switch it off all the excitation sources, and only in the dark conditions there will be detector, and slowly they start increasing the temperature. You can put a heater and do it, or simply open that valve so that liquid nitrogen escapes out, and slowly from minus 78 degrees centigrade, 78 Kelvin, it will start coming to the room temperature. When it starts coming to that one, slowly that's increasing of temperature. Then when they start vibrating, and slowly the photons that are absorbed and they are present in the higher energy state, they try to come down. So at particular temperature, with that one we can, how many photons have come up with the detector, whenever it shows some glow curve, it is called some glow curve, area under the curve and other things you can estimate, and you can find out what type of defects that are present. So that's the calculation part one can do. So this is the cryostat in this. So impurity levels, as I told, either you dopant is in little quantity, if you dope it is called dopant. 2% or less than 2% if you dope in any material, it's called dopant. If you put 5%, 10%, then it's called impurity. We actually research scholars, they use very loosely about this dopant or impurity. Sometimes they write dopant, and sometimes the same paper they write it as impurity. The difference is, if it is less quantity, less than 2%, you have to write it as dopant. If it is more than that, 10, 15% like that, then it's called impurity. And if you write 50% dopant, it is wrong. 50% impurity is also wrong. 50% you are adding means you are alloying it. It's a basic, it becomes one of the component of the system. Okay, so like that one has to use it. So you can estimate the shallow impurity levels or impurities that are present in the system. This is a simple example. You see zinc sulfide. Zinc sulfide is having a band gap of 3.6 electron volt. But if I try to dope with a copper ion, so it's quantum dots of zinc sulfide. If I dope with copper ion, I can get green emission. But same zinc sulfide, if you try to dope it with silver ions, then I can get blue emission. Same zinc sulfide, if I dope it with manganese, I'll get orange red at 590 nanometers. So the interesting thing is in photoluminescence, like if you have a high band gap material or insulating material or a wide band gap semiconductor, it is good because same material we can create many number of colors. If you have silicon, what is this? Silicon is also semiconductor. Silicon, germanium, 0.7 electron volt. Okay, here it is 3.6 electron volt, and silicon it is 1.1 electron volt. So what is the colors you can bring it? You cannot bring because 1.1 is so small. Even if you dope something, 1.1 itself we cannot see. Okay, so it should be 2.4 or 2 electron volt, then only our eye can able to see. Okay, so in that one 1.1 electron volt itself is so small, and whatever you dope it, like p-type doping, n-type doping, whatever you do in silicon, so we cannot visually we cannot see whether it is being doped or not. Okay, so if you want to see photoluminescence, you should have wide band gap semiconductor, at least 3.5, 3.6 electron volt gap, or more 6 electron volt like insulator. Then you can play with various dopants. You dope this one, you will get one color. You dope with some other element, you will get different color, and so on. Okay, that is for the doping. And if you don't dope anything, you create defects, then also you will get distribution, and then also you will get color. In both the ways you can detect. Okay, see the excitons that using the photoluminescence excitation spectrum, you can able to detect what are the excitation wavelength that is responsible for it. Okay, if time permits, we'll show once again those things. Exciton is nothing but the electron hole pair, conjugated pair, which moves around in a semiconductor. So usually we use the term called quantum confinement. In most of the nano studies, you try to listen this word. Is it not quantum confinement? What is quantum confinement? Anybody? You see, whatever peculiar property you see in the research paper, you write it, it is maybe due to quantum confinement. We don't know what is quantum confinement, but we will try to write it as all these effects may be due to quantum confinement. See, quantum confinement means if the exciton Bohr radius you can calculate for a bulk material. Suppose you have a bulk crystal like zinc sulfide only. So zinc sulfide is having a band gap of 3.6 electron volt, and exciton Bohr radius, using this formula you can calculate quantum mechanically. You can calculate the band gap as well as you can calculate the exciton Bohr radius, EBR it is called. Here it is not mentioned, maybe here. Exciton Bohr radius you can calculate with the rest mass of the hole and electron, and when you just substitute here, you will get the exciton Bohr radius for any particular material. The exciton Bohr radius for zinc sulfide is about 2 electron volts. No, not electron volts. 2 nanometers is the exciton Bohr radius. Suppose if I make a material lesser than that one, if I make zinc sulfide lesser than exciton Bohr radius, then I can able to see the quantum confined effects in that one. How is it possible? Like imagine like exciton Bohr radius of any bulk material is a standard one. So 2 nanometers I told means the distance between a hole and an electron is 2 nanometers. Suppose I made zinc sulfide lesser than 2 nanometers, like 1 nanometer particle I have made, quantum dots I have made. That means this thing is squeezed and is put in that one. It should exist in the material. It cannot be out of that. Exciton Bohr, you have that exciton should be present in that one. Means the size is this much, but your particle is this much. But still that particle should have this. So the exciton is confined and is present in that. So that is called quantum confinement. Got it or not? You can calculate exciton Bohr radius for any material. Suppose 10 nanometers, suppose a compound material you are working, the exciton Bohr radius is 10 nanometers. If you make the same compound lesser than 10 nanometers, then essentially what you see that exciton Bohr radius is squeezed and is present inside that. That's why it will show some abnormal properties. So there could be three types of thing. One is strong confinement. Like you have the exciton Bohr radius this much, you have particle very small. So this much is to be squeezed and present in that small size. So it shows very strong confinement. So very abnormal properties in quantum dots you see is because of strong confinement. Second one is weak confinement. Suppose your exciton Bohr radius is this much size, like let us say 5 nanometers, and your particle size is also 5 nanometers, 5 to 6 nanometers, near to that one. So it is easily fitting into that with a little confinement. So that is called weak confinement. Okay. So strong, medium you can say, medium confinement. Weak confinement is the one, suppose your size is this much and your particle is this much. So easily it can be there inside with less confinement effects, or weak or poor you can say. So depending upon the size of the particle what you are making, but any preparation method you adopt and try to make the nanomaterial, try to calculate Bohr radius. And if the exciton Bohr radius, once you calculate, or you can check in the web also, in the internet, what is the exciton Bohr radius of this particular compound, and to find out that, then you estimate the size, then you can compare. Then only after comparison only you can able to know whether it is strong confinement or weak confinement. If you want to understand more about this one of my papers is there, confinement effects in zinc oxide nanomaterial. Put it here. No, I've not shown it here. In nanotechnology, long back in 2008 or so, it was published in the journal IOP Nanotechnology. Confinement effects in ZNO quantum dots. That's the title of the paper. Okay. In that one, strong, medium, and weak confinements of zinc oxide particles have been very clearly established. Okay, there you can find out. So see, you can see the absorption shift, like smaller particles to the bigger particles in diameter. This is using photoluminescence only, you can able to estimate this. This is about the emission, PL emission, and depending upon different sizes you can able to see the same. This is all zinc oxide material only. I have done extensive work on that. You see the precipitated powders also, they are quite strong photoluminescent in nature, and we have got lot of appreciation for this, because usually when you type in Google saying that quantum dots, you'll see cadmium selenide and cadmium sulfide, different colors you will see. You don't see zinc oxide. We are the first in tuning the colors in zinc oxide depending upon the sizes. So for that one we got many appreciations for that, international appreciation. So fluorescence spectrometer, you have many things like a light source and a monochromator where the grating or prism will be there, which will select one wavelength which will fall on the sample cell, and that will be measured. Okay. So there is a thing called, sometimes you can use gratings also instead of prism. Gratings also you can have and measure it. And there is another thing called time resolved emission spectroscopy. Time resolved in emission spectroscopy is one where you can find out the rest time of electrons in the trapped state. Suppose it has excited to the conduction band and it has come back to some level, some dopant or something, that level before it coming back to the valence band. How much time it is residing in the excited state? We know that in conduction band 10 power minus 8 seconds is the standard one. Every electron will go and 10 power minus 8 seconds it will come back to the ground state. But trapped states are either shallow traps or deeper traps. So various traps can be tuned. So the resting time of an electron in the trap state will vary. So if you want to estimate that one, then time resolved spectroscopy technique is the one where you can do it at room temperature and low temperatures also. And with that one you can calculate the quantum efficiency and fluorescence lifetime also you can. So these things you can do. And the luminescence spectroscopy is a very interesting and widely used technique where you can do spectral measurements like excitation, emission spectrum and so on. And you can measure the lifetime, that is called the lifetime of time resolved spectroscopy or lifetime measurement, where fluorescence lifetime, phosphorescence lifetime you can measure, and polarization measurements also you can do, and some miscellaneous like quenchometry and other things for organic those who are working in organic molecules, they can work. So many things can be done with fluorescence spectroscopy. Okay. There is another system called TOF SIMS, time of flight secondary and mass spectroscopy. And this is another interesting case where, and laser SNMS, secondary neutron mass spectroscopy. So these are little sophisticated techniques where you can able to estimate or quantify the elements that are present in that one. So every vibration has a particular frequency and they can estimate the composition. Suppose you made some material and you want to estimate. Okay. So with these graphs it is difficult to say that there are many compounds that are even organic, like binding also. If you have put a small organic binder to make a pellet and that also comes out as a signal, then how to estimate that one? So there is a in the same there is a system called correlation analysis. Suppose you assign maroon color to manganese and zinc some blue color, and the overall sample is looking like this. It's a mixed color. If it is showing a mixed color, that means the distribution or the dopant, manganese is the dopant. So manganese has been dissolved or completely, very uniformly it is being dissolved. So if you take a manganese versus zinc spectrum, it shows like this. So this is with laser TOF SIMS only you can able to do that one. So not only the elemental measurement, but also mapping. You can see, I am unable to understand with the graphs. Let me show pictorially. So immediately it will show like this. So it's a, if it is at 45 degrees angle, then that means that the doping is very, very uniform. I'll show another example where the uniformity is not proper. For example, this. So this is a strontium aluminum oxide doped with europium. Europium and dysprosium also. Two dopants are there. So strontium blue color is given, europium dysprosium is green color, and aluminum as red color. So you see the combination here, it is not proper. See, somewhere only blue it is seen. That means only strontium oxide is present. Somewhere this green is there. That means europium is somewhere lying here. And somewhat red portions are there somewhere. That means only aluminum oxide is present. That means whether you, while making the sample or grinding or preparation of that sample, it was not uniform. So it shows the distribution. And you show the aluminum versus strontium, it is not following the 45 degrees angle, very scattered. And similarly aluminum versus dysprosium, because both are 3 plus ions. So the dopant dysprosium in aluminum also, it is not following. Means with this spectrum or the graphs profiles, you can simply say that sample is not a good sample. Of course, the elemental simply no need to have a uniform mixture. Even if you mix it little bit and give for that laser SNMS or top sims, you will get the composition. But really, it is doped or not? How will you know? Only with these profiles only you will be able to know that. Okay, this is the long back we have published this paper in 2005. So in again in nanotechnology, laser top sims and laser SNMS investigations of dopant distribution in nanomaterials, nanophosphors. Okay, this also you can. Let us stop it here. Few more techniques are there anyway. I'll come back to you after some time. It's already time is up. So we'll move to the physics department. One of my research scholars will take you there. Okay. So their demonstration, which I have shown the very first slides. So zinc oxide, probably I think they are planning for zinc oxide. They will tell you. So here I did not mention you how to make the redox mixture. I simply said nitrates are oxidizers and urea is reducer. Okay. Suppose you want to make certain compound, how to make it. So that explanation they will provide you. You can ask questions and you can make a note about those things. Okay. And one of the simple thing they will demonstrate. They will mix it in front of you, and that slurry with a beaker. They will put it on a furnace. Okay. And then you can, if you want, you can take video also, and you can watch how exactly it happens. It's an explosive type of reaction. Don't be very near to that. As I told, if the flame lasts for longer time, little more time, there could be an explosion of glass beaker. So if somebody hurt, I am not responsible. So little make a U type of thing near that chamber so that everybody can see. Okay. And my scholars, they will take precaution in doing that, and they will demonstrate you the making of nanomaterial. Before that, they will take you. See, as I told, it's a explosive type of reaction. All nitrates are explosive. Okay? Even when you talk about bombs which are dropped, okay, Hiroshima, Nagasaki, and all. So they all contains this TNT, trinitrotoluene, nitrogen compounds. Okay, all nitrogen compounds are oxidizers and they are very dangerous. Nitrates, what we use in the laboratory, we are using in very little quantity, so they are not that much dangerous. So what you can do is, suppose you want to see the auto combustion process is very good for oxides because we are giving oxygen to particular system. So oxides, any oxide, whatever you name it, whether it is a binary oxide or a ternary or a quaternary or multiple oxides also you can make it. That is first thing. And only thing is, suppose I have a zinc oxide bulk material, bulk powder, micron powder, but I want nano of that one, let us say. So take that zinc oxide and dissolve it in nitric acid. You will have zinc nitrate. That zinc nitrate you add urea, will become a slurry, I mean the transparent liquid. That you put it on furnace and you will have zinc oxide with nano form. How it is, why it is nano, and how much nano, or what is the shape and structure, you have to go with XRD and some other SEM and other things. Morphology, usually you will get spherical morphology, but you know zinc oxide can exist in many forms. But here in zinc oxide, mostly because the surface energy of a spherical particle is minimum, so it will try to have a minimum entropy. So all particles will be spherical, near spherical in nature. Okay. So if you want different structures, you can play with the fuel. See, instead of as I told, instead of urea, you can use alcohol. Alcohol is also combustible. Glycine, citric acid. tartaric acid. So these are very easily available chemicals. Okay, non. Yes, different morphology. And there are two types of combustion. What is flame combustion, flameless combustion. So in both the cases, see, if you give proper atmosphere, you will have flame. That's called flame combustion. If the ratio is not proper, then also you will have combustion. Like instead of carbon dioxide, carbon monoxide will come out. Okay, but combustion will takes place. Though that combustion product, flameless combustion also, like if you use glycine, you never get flame. But suddenly it will kick out the lid which you have put it, and you see this tiny particles floating around, and some are there in your beaker. So if you try to see that one, you will get finest particles, like in few nanometers you will get it with glycine, but you never get flame. Okay, so depending upon the redox mixture, the type of mixture, like see, you have kerosene also, you have petrol, you have diesel, okay, you have alcohol, whether all will burn with similar thing? No. So similarly here, if you change the fuel, you will change different shapes, morphology will change. But for urea, what I have seen is more or less it is spherical, where you can get little flame, and you will be amazed to see that in a beaker can you make the nanomaterial with a small stove or a hot plate. So that is the idea of showing you this. Okay, any other doubt in this? You can play with the pH also, pH of the solution. Okay, the starting temperature, like heater, if you are putting on a hot plate, it will be around 300 degrees centigrade or 350 degrees centigrade, isn't it? Suppose you put on a furnace at 800 degrees centigrade, like preheated furnace. Take the solution, put it directly inside. See why I am asking you to put it on a preheated furnace, preheated beaker, to avoid the evaporation of urea what you are adding. So if you put it inside and start switching on your furnace or this thing, slowly it will start boiling. By the time it reaches high temperature where it should ignite, by the time half of the water and urea also will go out. So for here also, while the explanation, they will tell you we are adding stoichiometrically whatever is amount of urea is required, we are adding double. Why we are adding double? Because with some of the thing is lost, even though we are putting a lid, some of the urea is lost. By the time after the losing also, when it forms a jelly type of thing, so then it contains similar required composition. Suppose you don't want to put anything extra, what you have to do? Because take this nitrate and put little water. You don't know exactly how much water you need to put. Okay, you put little 1 ml or so, and then you have added urea. Urea also for dissolving you are putting water. So excess water you are putting. So what you have to do is you take that clear solution, put it in an oven for overnight without lid, maybe 60 degrees centigrade. So in the night, so overnight if you put it, all excess water will evaporate and it forms a gel. Then you can put that one in on the heater or furnace, you will have your nanomaterial done. But if you want to do now, we cannot have that much time, na? So if you make it, and if I ask you to come tomorrow, half of the people will not come. So in order to save our time, we are adding excess urea and let it boil here itself, and let it go little bit. But by the time it jellifies, and you will have enough urea and nitrate mixture, which is highly combustible, and it catches fire in a beaker. Okay, so first you observe that practically, you see that, and then you can post on that questions to my research scholars also. They have done enough experiments on that. Still, if you are not satisfied, my email is there. I'll just put it on the very first slide. You can write to me that harnath@nitw.ac.in. I'll respond to that. Okay. Right. Thank you for your kind attention.